Okay, welcome back to topic 1.8. In this video, we're going to focus more specifically at how to make ionic compounds, or how ionic compounds form. Remember, an ionic compound is a bond between a metal and a non-metal. If you haven't done so already, please go ahead and write the charges above the particular groups as you see them here on your own labeled periodic table. This is going to be very important and helpful when looking at making ionic compounds. Group 1 elements will always form a 1 plus charge. Group 2 elements will always form a 2 plus charge. Group 3 elements will always form a 3 plus charge. That is because each one of those groups are in the section of the periodic table known as the metals. We will not worry about the transition metals or the lanthanides and actinides. Because they have electrons in either the d orbitals or f orbitals, things get a little different with them, and it's beyond the scope of this course. Group 4 is a pretty neutral group. They don't like to either gain or lose electrons, so they'll pretty much stay the way they are. Group 5 forms a -3 charge. Group 2 forms a -2 charge. Group 1 forms a -1 charge. And then Group 8 will not form any charge at all because they already have a full valence shell. Let's take a look at our first example. This is a little similar to the one that you saw in the earlier video. What element is this, and what will its charge be when it forms an ion? The electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. You should be able to identify this element as potassium, or K. So that's the first part of the question, is figuring out what element is this, and what will its charge be when it forms an ion. If we come back here to our periodic table, we can find potassium here in the first group that forms a 1 plus charge. So potassium will form a 1 plus charge. You can just as easily write this as K 1 plus as well. Both of them are considered correct. This, by the way, is not the electron configuration for the ion. This is the electron configuration for the neutral atom. Okay? If it was the electron configuration for the ion, the question would have to tell you. Here's a second example. Go ahead and pause the video and work through this one. Okay, what element is this, and what will its charge be when it forms an ion? 1s2, 2s2, 2p6, 3s2, 3p5. You should be able to identify this as chlorine. And what charge will chlorine form when it makes an ion? If we come back here to our periodic table, we'll find chlorine in group 7, which forms a -1 charge. So we can write chlorine as -1, or we can do chlorine as 1-, or you could even do, because it's a 1, you could just do Cl-. Either one of those work. You can only do the minus sign without the number if the charge is 1. So we could just as easily as over here done this with potassium. Either one of those work. And again, you can only leave the number off if the number is 1. Alright, now let's look a little bit more closely to what ionic bonds are, how do they form, and what are the laws that govern their formation. Remember, the ionic bond forms when a metal bonds with a non-metal. You should already know where the metals and non-metals are on the periodic table. The law of definite proportions says that they will bond in a fixed ratio such that their overall charge is 0. So when they come together to form the compound, the charges must add together to be 0. Let's take a look at the first example here. What is the formula for potassium chloride? Well, how do we figure this out? Let's first go ahead and determine what will the charges be for each one of these elements. Potassium is in group 1, so it will form a 1 plus charge, or a +1 charge. Chlorine is in group 7, so it'll form a -1 charge. We now need to determine how many of each of these elements we need, such that the overall charge at the end is 0. I'm going to start by putting 1 potassium in my box here, And that means so far the total positive charge is 1. Plus 0 that I have over here equals a total charge of positive 1. This isn't working. This total charge here needs to be 0. So let's go ahead and try to balance this out with a chlorine. Now, the contribution of negative charges is -1 so far. The total contribution of negative is -1. If we add together +1 plus -1, we now get an overall charge of 0. So we have figured out how many of each one that we need. The basic skeleton for this formula is going to be KXCl(Y). Well, what are the numbers for X and Y? How many potassiums did we use in the box over here? We just used 1, so we'll just write K to represent the 1 chlorine. How many chlorines did we use? We just used 1, so we'll write 1Cl. And this, ladies and gents, is the formula for potassium chloride, KCl. Let's take a look at another example. Go ahead and work on this one alone, pause the video, and then come back when you're ready. Okay, what is the formula for sodium fluoride? We know sodium's in group 1, so it's going to have a +1 there. Fluorine is in group 7, so it'll have a -1. We now need to start adding sodiums and fluorines into these boxes here until this comes out to 0, the total charge. We'll start with 1 sodium, and then so far our charge is +1 over here. Let me do that in green to be consistent. And then why don't we start with 1 fluorine, so that the total negative contribution is -1. And then we ask ourselves, does -1 plus +1 equal 0? It sure does. We know that the skeleton formula is going to be NaXFY. How many sodiums did we use? We used 1 total, so we'll just leave it with Na. How many fluorines did we use? We just used 1, so we'll have 1F. That means the overall formula for sodium fluoride is NaF. Let's do this next one together. What is the formula for aluminum oxide? Okay. If you look at your periodic tables, aluminum is in group 3, so it has a 3+ charge. Oxygen's in group 2, so it has a 2- charge. Let's go ahead and start filling in our boxes here with aluminums and oxygens until such that this charge comes out to 0. Okay. Let's start with 1 in each one. We'll start with 1 aluminum at a 3+ charge, which means we're getting a total of +3 so far contributed via the positive side, and we'll start with 1 oxygen, which means we got a -2 charge. Okay. Well, -2 plus +3 is +1. This does not add to 0, so we are not done yet. We're going to need to start adding more. Okay. Let's add another aluminum in. We now have +6 on this side versus the -2 on this side. Not quite there just yet. I don't want to add any more aluminums right now because it's higher than the oxygen. So let's try to get the oxygens to match +6 somehow. Okay. If I put another oxygen in here, the total contribution to oxygen, or the negative side, is now -4. We're almost there, okay? Again, I'm not going to add any more aluminums because if I add another aluminum, this is going to go up to +9. I need to try to get this to match this now, since it's at the lower charge. Let's see if I add another oxygen in here. I now have a total contribution on the negative side as 6 because -2 plus -2 plus -2 is -6. Hey, -6 plus +6 adds to 0. Now that we know the charges add to 0, let's figure out the entire formula. Basic skeleton of the formula is ALO, ALXO, or Y. How many aluminums did we use? We used 2, so we're going to have Al subscript 2. How many oxygens did we use? We used 3, so we'll have O3, and this is the formula for aluminum oxide. Alright, let's try strontium. You try strontium sulfide on your own, and then we'll come back and discuss. Okay, so for strontium fluoride, strontium is in the second group, so it has a +2 charge. Sulfur is in the it's in group 6, yes, group 6, so it has a -2 charge. Let's start filling in the boxes now with sodiums or strontiums and sulfurs until we get a balanced charge of 0. We'll start with strontium, +2 charge. So the total contribution to the positive side right now is 2. We'll now put a sulfur in there, or sulfide, because it's an ion. And now the total contribution on the negative side is 2. Is -2 plus +2 0? It sure is. That was rather easy. Let's go ahead and write the formula. SRX, SY. We used 1 strontium, so it's just going to be SR. We used 1 sulfur, so it'll just be S. You might be tempted to do SR1, S1, even though that is technically correct. Get out of the habit of using the subscripts as 1s. Okay, please get out of the habit of that. It's a little elementary, it's a little too CP chemistry, and we're in the AP class now. It's much better and much preferred to write it without the 1s. Okay, I am so sorry to have to teach that to you the hard way this way. There is actually a much easier way to figuring out these formulas, but I did have to go through the principle first, okay? Here's the easy way. It's also known as the crisscross method. You guys already know that aluminum oxide is Al2O3. And you already know that aluminum contributes a +3 charge and oxygen contributes a -2 charge. You might notice that these numbers right here are actually the switched charges. Okay? So the way we get the formula, the easy way, is we just take this 3, move it down here, take this 2, move it down here, not bringing the signs with it, so it's actually Al2O3. Makes it much easier. Notice I didn't bring the signs with it. This tells you that you need 2 aluminums for every 3 oxygens to make a neutral ionic compound. But a word of caution. What if you get a situation like this, where they both have the same charge? Okay? If we do the crisscross method, this 2 will come down here, it'll be Be2. This 2 will come down over here, it'll be O2. And then technically we have Be2O2. This is not allowed, okay? You have to reduce it to the lowest possible integers. If you end up with a situation like this, you need to find the least common multiple and reduce everything. The least common multiple between 2 and 2 is 2. So we will reduce both of these by 2, and the true formula is BeO.